Hello everyone. So in this video, we'll introduce a term called Wronskian of two functions. Okay, so let's define what is a Wronskian of two functions. Suppose you have two functions, f of t and g of t. Then Wronskian of f and g, denoted by w of f comma g, is again a function of t, and that is calculated as follows. A determinant of the first row is f of g of t, and the second row is f prime t g prime t. So of course, you have to see that only those functions you can find on scan where these two things exist, f prime and g prime. So this is determinant, so it's nothing but f of t g prime of t minus g of t f prime of t. So this is the Wronskian. Okay. So suppose y1t and y2t are two solutions of a differential equation. So our differential equation is our standard differential equation. Okay, so let us write it. Are two solutions of pt y double prime plus qt y prime plus rt y equal to 0. So this is our standard one with initial conditions y0 y prime of t0 equal to y0 suppose prime. So suppose y1 and y2 are solution of the differential equation star, then the solutions are called a fundamental set of solution. Then the solutions are called a fundamental set of solutions. So let me highlight this word, fundamental set of solutions. If the Wronskian of y1 and y2 is not equal to 0. So this is the condition. Okay, and the general solution, this you know already. The general solution is given by yt equal to c1 y1t plus c2 y2t. C1 and C2 are constants. Okay. Next, I will give two facts on Wronskian. So the first one maybe. So suppose we start with two functions f and g. Okay, so let me write it down. So ft comma gt, two differentiable functions on some interval, say I. Then if the Wronskian f comma g at some point t naught is not equal to 0, where this t naught belongs to that interval I, then f and g are said to be linearly independent. Then f of t and g of t are said to be linearly independent on I, the interval I. The second condition is if ft and gt are linearly dependent on I, then it is a somewhat converse, you can say, not exactly converse of the first statement, but somewhat converse. Then the Wronskian of this thing equal to 0 for all t belongs to I. So you have to see the difference between two statements. So if there exists one point in the interval t such that this is not equal to 0, so Wronskian at t naught is just evaluating the Wronskian at the point t naught, the Wronskian. Okay, so it is not equal to 0 at one point, then we call linearly independent on t. And if it is 0 for all t belongs to I, then it is said to be linearly dependent. Okay. So let me highlight these two terms. So linearly dependent and linearly independent. Okay. So let us go through some examples to see this fact. Okay, so suppose we have a first function f of t as 9 cos x and okay, so it's f of t and g of t as cos square t minus sin square t. Then let us check what does the Wronskian give us. The Wronskian of f comma g, we know how to find out. So it's 9 cos t, then derivative of it, so minus 9 sin t cos square t minus sin square t. Right, so it is 2 cos t sin t minus sin minus 2 sin t cos t. That is fine. So this is equal to 9 cos t minus 9 sin t cos square t minus sin square t minus 4 cos t sin t. So I can write sin to t, but again I have to simplify, so I'm not writing that. It's minus 36 cos square t sin t minus, so it's plus sin t cos square t sin t. So it's minus, so it's plus, right? Okay. So 9 sin cube t. So minus 36 minus 9 is your 27 cos square t sin t minus 9 sin cube t. So you can take minus 9 sin t common, then you will get cos square t plus sin square t. So I've taken only 9, so it's 18 remaining cos square t sin t. So this is equal to 1. So it's nothing but minus 9 sin t minus 18 cos square t sin t. 1 plus 2, this thing. So it is not equal to 0 if sin t is not equal to 0, right? So yes, so this Wronskian of if t is not equal to 0, if and only if sin t not equal to 0. So if we have an interval where sin t is not equal to 0, then they will be linearly independent. Okay. So this was the idea. This is the definition of Wronskian. Wronskian of two functions is given by this thing, and the solutions y1 and y2 forms a fundamental set if the Wronskian at t is not equal to 0. Then we have these two conditions when the two functions are to be linearly independent and dependent, and we saw an example how to compute Wronskian and how to conclude that where they're independent or dependent on a given interval. Okay, thank you.